In the last video, we introduced a few new group structures that are built into the software. And in this video, we're going to look at two more new algebraic structures that can be used. The first one I'm going to look at, if you go to the Group tab, scroll down to SN here. And this is what's known as the symmetric group or the permutation group on n letters. Okay, typically the smallest one of interest we'll look at is n equals 3. And what S3 does is it takes three objects. Usually we just think of these as the numbers 1, 2, and 3. And it's the group of permutations or ways to rearrange the numbers 1, 2, 3. If you've taken a discrete math class or an abstract algebra class, you may have looked at permutations. They're really functions because they're rearranging things. So the group operation in this case is function composition. In general, for an n-element set, there's going to be n factorial permutations. So S3 in this case is going to have 3 factorial or 6 elements. All right, so to create a PascGalois triangle over this group, I'm going to go here to the 1D automaton. All right, and we are going to have to change the seed. Now, this is where it gets a little bit nuanced if you haven't seen this notation before, but we need to enter permutations into the system, and we use what's called cycle notation, which is a standard way to represent permutation, and it works as follows. Since I'm in S3 and I'm rearranging the numbers 1, 2, and 3, I'm just going to type, say, the first number I want to look at, which is 1 in this case, and let's say I map that to 3, so I'll type 3 next, and then after that I want to map 3 to 2, and then I'm going to close that off. Oop, I misspelled 2 there. There we go. So this is the permutation and cycle notation that maps 1 to 3, 3 to 2, and then 2 back to 1. Note the spaces between 1 and 3 and 3 and 2. Those spaces, you do need a space there so the system can distinguish the number. All right, so that's one of the 6 permutations, and we're just going to put that down both sides of this triangle, which is going to give us that. All right. Now, we're in a group with 6 elements, 6 permutations, and clearly we're not getting all 6. As we've seen before, sometimes one group element is not going to be enough to generate all of the others, and the permutation groups are definitely instances of that. So in general, we're going to need more group elements. So I'm going to go to the seed and add a second one. And let's say I do the permutation 1, 2. So what this is going to do is, this is in cycle notation, the permutation that maps 1 to 2, 2 to 1, and since we didn't explicitly list 3, we assume 3 maps to itself. It still has to map somewhere, so if it's not listed, we assume it maps to itself, and that does give us a well-defined permutation. So now we'll look at that image. And this one, you see kind of a lot of disorder, some almost seeming randomness at times. And that's because of the group structure of S of 3 that's causing that. We could add some more rows. So let's go up to 200, just kind of pick that randomly. And now we're starting to see a little more structure. It's not clear what. We still see the randomness, but maybe something's happening beside the scenes. So I'm going to go up a lot more rows now. And let's say I want to go to over 1,000 right here. So let's draw it. In this case, wow, so something's definitely happening. If you know a little bit about group theory, or eventually you're going to learn some, that'll help explain what's going on in this image. But for now, the short-term moral of the story is, sometimes when you're looking at these structures with a small number of rows, you don't see much mathematically. It can look fairly random and not much interesting mathematical structure going on. But if you go further out the system like we did here, yeah, there actually is some really interesting hidden structure. So now let's try a different version of n. So I'll jump up to S4. So this will be the set of all of the group of all permutations on the set 1, 2, 3, 4. There's going to be 4 factorial or 24 elements in that set. Let me scale back the number of rows real quick. Okay, maybe just say look at 100. And I'm going to keep the seed as I had before. So that's still it. Those are still valid permutations in S4. So let's look at the image. Okay. And notice it looks a lot like the previous image, and there's only 6 colors. And what's happening here is even with these 2 permutations now in S4, they're not enough to generate all 4 factorial or 24 elements. If you play with some different seeds, what you'll see is lots of combinations of seeds won't generate all 24 colors. But if you try enough, eventually you'll stumble across a few that will. So for example, let's try this one here, and I'm gonna do that there. So those are 2 permutations in S4. Redraw the image, and notice now, yeah, we do get all 24 colors or all 24 group elements. A very disordered picture, not a nice symmetric image, at least at this scale by any means, but we can still, generate a PascGalois triangle using these group elements. Back when we were doing the mod-n structures using addition mod-n, you may have wondered if you could use multiplication mod-n and do something similar. And the answer is yes, and we have that built into the group table right here. If you scroll down to Zn under multiplication, the Zn is the same set as before, but now we're just replacing the addition mod-n with multiplication mod-n. Technically, Zn is not a group under multiplication mod-n. It doesn't satisfy all the group axioms, but it does turn out to give you something called a ring, which is a set with 2 operations, an addition and a multiplication, that satisfies for certain properties. For now, we're just going to focus on the Z mod n under multiplication and at least draw some images with it. All right, so let me go to the 1D Automata tab. I'll do a smaller number of rows. Let's see, which actually group did I pick? Let me switch this to mod 5. So this is going to be multiplication mod 5. All right, and for my seed, let's say I just want to put 2 down both sides. All right, so I can do that. And I get an image there. Now that looks much like some previous images we've seen with the mod-n structures under addition. But keep in mind, this is really a multiplication. So something a little bit different is going on, at least under the hood. And that's something you can investigate. We can tweak the seed if we want. Let's say I want to do 2 down one side, 3 down the other. Get something that looks like that, but again, it's not much different than images we've seen with the regular mod-n groups under addition, even though the operation's different. However, with other combinations of the modulus and seed values, we can see some new behavior. So let's look at that right now. I'm going to jump up to mod 12. So matrix multiplication mod 12. And let's say for seed, let me do 8 and 10. So we're putting 8 down the left side of the triangle, 10 down the right, and then using multiplication mod 12 to generate the interior. And you get something like that. So a little bit different, but maybe not too surprising yet. Notice we did not get all the colors right here. We only got, there's 12 elements in this set. We only got 4 of them back right here. We can play with the seed a little bit. Let me just change the 8 to a 6. All right. Now, in this case, something different happens. We've not seen this behavior yet. Notice all the black in the middle. If you look on the right at the color scheme, black is actually 0. So what's happening right here is, since we're doing multiplication, if we ever multiply 2 things and get 0, Once a zero shows up, zero times anything, zero. So then the zeros just propagate. So this is something that can sometimes happen depending on your modulus and your choice of seed in these multiplication mod n type triangles. And that's something worth investigating further, so I won't say too much more about it, but something that you can have fun playing.